purpose of this picture is to show how to trace malfunctions in the C-1 Autopilot by the process of elimination. It is assumed that the audience is thoroughly familiar with the C-1 Autopilot and understands the operation of the various units as shown in the preceding pictures of this series. The servo motor, the directional stabilizer, flight gyro, and the amplifier. A thorough study of these films is essential in order to trace down malfunctions through the process of elimination. By using this tabletop mock-up, the device by which we will demonstrate the principles of ground check and troubleshooting on the C-1 Autopilot, we can also explain the process of elimination. These units have been arranged so that an overall check of one component against the others can easily be followed. In each axis, there are 4 component parts: power, amplifier, bridges, and servo. A malfunction occurs when any of these links fails to operate perfectly. In troubleshooting, if 3 of the components can be eliminated as sources of trouble, the malfunction can be traced to the remaining ones. In this setup, we have the flight gyro, stabilizer, amplifier, and all other elements, including the 3 servos and the junction box. This junction box is the central headquarters of the autopilot wiring system. It will be a good idea to study this unit for a moment, as it plays an important part in running down many malfunctions. In this particular junction box, there are 6 individual terminal blocks, each identified by a letter: A, B, C, D, E, and F. Separate terminal numbers from 1 to 10 are located on each of the 6 blocks. It will be easy to identify each individual terminal by its number and the letter of the block on which it is mounted. For instance, number 1 on D block and number 9 on A block would be identified as D1 and A9. By checking the diagram, you can easily identify any of the terminals in the junction box. Let's say you are making a check through the circuit from E5 to F3. You would place a contact at block E, terminal 5, and at block F, terminal 3. By making continuity readings like this in the junction box, the problem of tracing malfunctions having to do with the bridge circuits and the wiring in general will be a whole lot easier. Your printed instructions should be followed in making the ground check, which is part of the procedure in tracing all malfunctions. Referring back to the 4 components, first make a check of the power, AC and DC. This includes a check of the battery, which supplies direct current, and the rotary inverter, which supplies the alternating current required by the system. After you are satisfied that the power source is functioning properly, make sure that power is reaching all of the units by checking the AN connectors. Always double-check the stabilizer AN connectors, as the stabilizer is removed and reinstalled more frequently than the other units. In ground-checking the bridges, you will have to make a very careful inspection of the pots on the flight gyro. See that they are electrically centered. Be sure the wiper arms have the proper tension and that the pots are clean. A check of the knobs on the control panel in the cockpit should be made. See that these knobs are centered properly, and tighten any that are found to be loose. Another thing, be sure none of the bulbs in the telltale lights are burned out. The pots in the directional panel of the stabilizer should be checked. This will include both rudder pickup and aileron compensation. The balance pot of each of the servo motors must also be inspected. All these pots in combination make up the bridge circuits of the Autopilot. Follow your bridge circuit diagram when an electrical check of the bridges becomes necessary. Only a part of the amplifier is used in any one of the three axes. This is actually three amplifiers in one unit. These two tubes and these two relays work in the aileron axis, this set in the rudder axis, and this pair in the elevator axis. Each of these three sections relays signals to its respective servo motor. Check all tubes. See that the prongs are clean and that the bases are properly locked in place. Then, check the operation of the relays. First of all, see that the points are clean. And then, make sure there is correct clearance between the points. After the servo pot has been checked, don't fail to inspect all spring adjustments, limit switches, and all other points listed in your tech orders. During the ground check, we can assume that all necessary replacements in any of the units will be made, and the parts adjusted for proper operation. But, in spite of all care in checking, malfunctions may occur in the Autopilot. Let's take an example. When the master switch is thrown, and the system has had time to warm up, the Autopilot does not function at all. None of the telltale lights in any of the axes glows. And further inspection reveals that none of the motors in the servos is running. The trouble could be caused by a burned-out fuse. However, in this case, the fuse is okay. So a check across the terminals of the master switch must be made. As you will find on your wiring diagram, this test can be made from B10 to E5. The meter reads full output. This indicates that the power is reaching the master switch. So remove the panel from the housing of the ACP. Then place the meter contacts directly across the terminals of the master switch. Here the meter again reads full output, with the switch open or closed. This indicates a defective switch. With a new switch installed, make a complete ground check. In this case, it is found that everything else in the Autopilot is okay, and that the trouble has been eliminated. Most malfunctions are indicated by incorrect action of the plane when it is being flown on Autopilot. During the ground check, it is found that 2 of the axes function properly, but that the lights in the elevator axis are dead, and there is no drive in the elevator servo. Since the aileron and rudder axes function, we can assume that the power is okay, and further, that the trouble is in the elevator axis. In checking to see if the elevator relays in the amplifier are sending impulses to the servo, we operate them manually. We find that by this method, signals can be relayed to the servo, causing it to drive in each direction, and that the elevator telltale lights respond. This means that 2 of the 4 components, power and servo, are eliminated, and that the malfunction is in either the amplifier or bridges. At this point, it will be necessary to use a diagram of the elevator bridge circuit so that the correct terminals in the junction box can be checked. In order to see if a signal is being relayed from bridges to amplifier, connect an AC voltmeter from D5, which is the grid of the tube, to any common ground, in this case, E5. With these contacts made in the junction box, and with just the master switch on, rotate the elevator centering knob. We find that the meter does not register any voltage when the knob is turned in either direction. This indicates that the signal from the bridges is not reaching the amplifier. Therefore, we can assume that the amplifier is not the source of trouble. Now, with power, servo, and amplifier eliminated for the time being, we can assume that an open, or ground, exists somewhere in the bridge circuit. Again, with the aid of the chart, we begin a continuity check in this circuit. Through D5 to E1, the volt-ohm meter indicates the proper resistance of about 500 ohms. This shows that the bridge through the ACP to the elevator compensation wiper in the flight gyro is okay. So we next take a reading from D5 to B9. This also shows the proper resistance, about 500 ohms, which means that the circuit from the grid through this side up to the elevator pickup wiper in the gyro is okay. But when reading B9 to C1, which includes part of the pot resistor, the meter shows a much higher resistance, or about 10,000 ohms. This indicates there is an open here between the resistor and wiper in the flight gyro. As the wiper is bent out of shape, a replacement is called for. Now that the malfunction has been corrected, a complete ground check of the entire system shows that all 3 axes are working normally, and the plane is again ready for flight. Now let's take up a situation where the ailerons do not put in proper corrections. Here is how we go about running down the trouble. With the ailerons at streamline, snap the master switch. Then turn out the aileron telltale lights. It is found that only one light is operating. But as the axis is not functioning properly, we can assume that the light that isn't burning is okay. So we extinguish the one that is burning. Engage the aileron brake switch, and again rotate the centering knob to observe the effect of this action on the aileron servo. It is found to move in one direction only. With the master switch and aileron switch on, check the amplifier output by pressing down on the relays in the aileron axis, one at a time. We find that this action puts in correction in the servo in both directions. Now, by the process of elimination, we have discounted the power and servo as sources of trouble. Since the bridge sends a signal to one side of the axis, we can also eliminate this, at least for the time being. This leaves only the amplifier to be checked. Apparently, the signal that should operate the aileron relays is not reaching one of them. So, it will be necessary to check the 7N7 tube in the aileron axis. First, turn off the master and aileron switches. Then, to test the tube, replace it temporarily with a 7N7 from one of the other axes. With the master and aileron switches on, the relays function perfectly, and the servo drives in both directions. With the new 7N7 tube installed and the malfunction in the amplifier corrected, all four components of the system are again functioning properly. Here is a malfunction where the turn control puts in right turn correctly, but the ship skids in the turn and keeps on skidding after straightening out on the new course. This skidding action means trouble in the rudder axis. So the other two axes can be eliminated in tracing this malfunction. As the first step, have the master switch on and turn out the telltale lights. As the lights react when the centering knob is rotated, we assume that the bridges are all right, and that the relays in the amplifier are operating on both signals. But the servo in the rudder axis turns in one direction only, then stops and will not return. So, by the process of elimination, the servo is the only component which can be the source of trouble. During inspection of the servo, all adjustments are checked, and all mechanical parts appear to be in perfect working order. But in checking back on the amplifier, we find that when the relays send impulses to the servo, only one of the operating solenoids is energized. When the other relay sends a signal, there is no motion in the solenoid to which it is connected, even though a meter reading indicates that the proper voltage is reaching this solenoid. This means that the solenoid in question must be checked. For this, we will use a volt-ohm meter. In order to check from this terminal to this terminal through the inoperated solenoid, the limit switch points must be broken on this side and this terminal removed. The meter reading shows that the circuit in the solenoid is broken, so a replacement becomes necessary. With this malfunction corrected and a complete ground check made, All four components in the rudder axis are again functioning properly, and the plane is ready for flight. In this film, it has been possible to show only a few representative malfunctions of the C-1 Autopilot. Others, which have not been shown, may occur from time to time. But in any event, if the process of elimination, as demonstrated here, is followed, the cause of any malfunction can much more easily be located than if a hit-and-miss procedure is used.